Hello everyone, myself Vinay Kumar. In this particular YouTube channel, I will be teaching physics, chemistry and mathematics starting from 8th standard till 12th standard. So in my previous video, I was actually teaching quadrilaterals chapter. So that was actually the part 1 video of this particular quadrilateral chapter, which is actually third chapter of 8th standard mathematics. So in this particular video, I will be teaching the remaining concepts which I have left in that particular part 1 in this particular part 2 video. So if you want to learn all this physics, chemistry and mathematics, then please do subscribe to my channel and stay tuned with my channel. So in this particular part 2 video, I'll be covering the remaining concepts of this particular quadrilaterals and the exercises 3.3 and 3.4 which is there in this particular chapter will be the part 3 video of this particular chapter. So in this part 2, I'll be teaching concepts which are remained. Coming to the new topic in this particular quadrilaterals, you are actually learning what is quadrilaterals in this particular section. So you have different forms of quadrilaterals. So any simple closed curve which is formed by a line segments, then that particular closed curves are actually known as polygons. So a closed curve, a simple closed curve which has been formed by 4 line segments, then that particular closed surface or that particular closed curve is actually known as quadrilaterals. So here there are like different quadrilaterals present. So we will go on looking one by one. So the first quadrilateral which we will be learning is trapezium. Trapeziums are those closed curves which has two opposite sides parallel to each other. So trapezium is also a quadrilateral which has 4 line segments in it, and any 2 line segments which are opposite to each other are parallel. So for example, this can be one particular trapezium. Here you can see there are 4 line segments present where these 2 line segments are actually parallel to each other. There is no condition that these 2 line segments should also be parallel to each other. Any 2 line segments should be parallel to, any 2 line segments which are opposite to each other should be parallel to each other in a quadrilateral. Then that particular quadrilateral can become a trapezium. So even a square can be also, a rectangle can also be a trapezium. Even a square can also be a trapezium, because here also you can see minimum 2 line segments which are opposite to each other are parallel. Here actually these 2 line segments are also parallel to each other, and these 2 line segments are also parallel to each other. There are at least 2 line segments which are opposite to each other are parallel. So here square can also become a trapezium, rectangle can also become a trapezium, and this particular figure which I have drawn is also a trapezium. Even you can have parallel lines like this as well. So this kind of image can also be a trapezium, where you can see 2 line segments which are opposite to each other are parallel to each other. There is no condition that other pair of line segments should also be parallel. At least one pair of line segments which are opposite to each other should be parallel, because in a quadrilateral you have 4 line segments and you will be having 2 pairs of line segments opposite to each other. So one pair, at least one pair should be parallel to each other. Then that will be a trapezium. So that's where rectangle is also trapezium, square is also trapezium, this is also trapezium, and this particular figure is also a trapezium. So if you have a quadrilateral like this, so this particular line is like this and this particular line segments are like this. So here this particular quadrilateral is not a trapezium, because this line is not parallel to this line and this line is not parallel to this line. So that shows there is no 2 line segments which are parallel to each other. So there is no pair which is actually parallel to each other in this particular quadrilateral. Hence this is not a trapezium, but this is actually a trapezium and this is actually a trapezium. So coming to the next form of quadrilaterals, there is kite. So what are kites? So in kites, the adjacent line segments of that particular quadrilateral should be equal. So if I draw a figure like this, so if I draw a quadrilateral like this, then this particular line segment should be equal to this particular line segment, and this particular line segment should be equal to this particular line segment. That means 2 adjacent line segments should be equal to each other. So if there are 4 line segments, then there will be 2 adjacent line segments. Like if you consider that as one pair, then the other pair of 2 adjacent line segments should also be equal. So you can see this particular side and this particular side are adjacent, and this particular side and this particular side is adjacent. So this is actually equal and this is actually equal. So such kind of figures, such kind of quadrilaterals are actually known as kite. So even a square can be a kite because a square has its adjacent sides equal. So here also you can see there is adjacent sides equal. So if you consider this as a square, this as a quadrilateral, here also you can see adjacent sides are equal and the other pair of adjacent sides are also equal. So coming to the next quadrilateral, you have parallelogram. So parallelogram is also a quadrilateral which has its opposite sides parallel to each other. So this particular image, if I like this particular figure, if I draw, then you can see this particular line is actually parallel to this particular line, and this particular line is actually parallel to this particular line. So in a quadrilateral, opposite line segments should be parallel. So what is the difference between trapezium and parallelogram is that in trapezium, if one opposite line segments are parallel to each other, then that can become a trapezium. But in parallelogram, like one pair of line segments which are opposite, because in a quadrilateral you have two pair of line segments which are opposite to each other. So both the pairs should be parallel to each other in a parallelogram. So if you consider these two line segments as opposite to each other, then they should be parallel to each other, and these two line segments are opposite to each other and they should be parallel to each other. Then only this particular quadrilateral can be known as a parallelogram. Even a parallelogram can be known as a trapezium. So parallelogram is a trapezium, but all trapeziums are not parallelogram, because in trapezium at least one pair of opposite line segments are parallel to each other. So that's why trapeziums are not parallelogram always, because other pair of opposite sides may be parallel or may not be parallel. But in parallelogram, both the opposite sides, both the pairs should be parallel to each other. So that shows parallelogram can be trapezium, but all trapeziums cannot be a parallelogram. Here, squares can also become a parallelogram because square has parallel opposite sides. So these two line segments are parallel to each other and these two line segments are also parallel to each other. Similarly, a rectangle can also be a parallelogram because opposite line segments are actually parallel. Both the opposite line segments, like both the pairs, are actually parallel to each other. This line is parallel to this and this line is parallel to this. So a rectangle can also become a parallelogram, or square can also become a parallelogram, and this particular diagram or this particular figure which I have drawn can also be a parallelogram, provided that opposite sides of that particular quadrilateral should be parallel. So now you know what is parallelograms. Based on this knowledge which you have on this particular parallelograms, you have certain properties. So let us actually concentrate on first property of this particular parallelogram. Opposite sides of a parallelogram will be equal to each other. So opposite sides of a parallelogram, I'll just write like this, are equal. So here we should actually prove opposite sides of parallelogram are always equal, because opposite sides of a parallelogram are parallel to each other, then they should be equal to each other. So this is actually property 1. Let us prove this particular property 1. So we are actually proving this particular property. So to prove this property, we will actually consider one particular parallelogram like this, and we will actually draw a diagonal for this particular parallelogram like this. So let us name this parallelogram as ABCD. So now we have a diagonal drawn from A to C. So now we have two different triangles. One is ADC and one is ABC. Now if you consider AB is parallel to DC, because AB is parallel to DC, we will actually name these particular angles which has been formed with respect to this diagonal. So let us name this as 1 and this as 2, and let us name this as 3 and this as 4. So we have 1, 2, 3, 4 as our 4 different angles. So here, since AB is parallel to each other, AB is parallel to DC, because in parallelograms opposite sides will be parallel to each other. So only when opposite sides are parallel to each other, then that can be a parallelogram. Now we are actually proving opposite sides of a parallelogram are equal. So here actually AB is parallel to DC, that is actually given information. So here, since AB is actually parallel to DC, this particular angle 2 and angle 3 will become alternating angles, because if we have a parallel lines like this, and if a line is actually passed through these particular parallel lines, then this particular angle and this particular angle will act as alternating angles. So these alternating angles will be equal to each other always. So these properties you have learnt in your previous classes. So here, since 2 and 3 are alternating angles, since 2 and 3 are alternating angles, 2 and 3 will be equal to each other. So angle 2 will be equal to angle 3. Similarly, since these two lines are also parallel, like AD is actually parallel to BC because that is also opposite sides. So AD is parallel to BC, hence you can see this as parallel lines like this, and there is a line like this which has drawn as a diagonal. So these two angles will also act as alternating angles. That means this particular 1 and this particular 4 will become an alternate angles for this particular AD and BC because AD and BC are parallel to each other. So here 1 and 4, angle 1 and 4 are alternating angles. So since these 1 and 4 is actually alternate angles, hence this 1 and 4 will be equal to each other. So these are alternating angles. So 1 and 4 will be equal to each other. So angle 1 is actually equal to angle 4. So in this particular triangle ABC and triangle ADC, so we have two triangles, triangle ABC and triangle ADC. So in this, one particular angle is equal, like the angle 2 is equal to the angle 3. So one angle of ABC is equal to one angle of ADC. That means here 2 is actually equal to 3 and angle 1 is actually equal to 4. So here triangle ABC has angle 2 and triangle ADC has angle 3, which are equal to each other, and in triangle ABC you have 4 and in triangle ADC you have 1, that is also equal to each other. 4 is equal to each other, and here you can see AC is actually common side of this particular triangles ABC and ADC. So according to SAS postulates, which you have learnt in your previous classes, here angle is actually, ASA postulate. So here angles are equal, two angles are equal and one side is actually equal to each other. So here according to ASA property, so according to ASA property of two triangles, here according to ASA property, this particular triangle is actually similar to, so triangle ABC is actually similar to triangle ADC according to this particular ASA property. So that shows here AB should be equal to DC and AD should be equal to BC, since triangle ABC and triangle ADC are similar triangles. So here AB is actually equal to BC and AB is actually equal to DC and AD is actually equal to BC. So this is actually DC. So AB is equal to DC and AD is equal to BC because triangle ABC and triangle ADC are similar triangles according to ASA property, because two angles are equal and one side is actually equal to each other in these two particular triangles. So other two sides should also be equal to each other. So according to ASA property, you are getting opposite sides of this particular parallelograms are equal. So here you actually proved that opposite sides of a parallelogram are equal. Hence it is actually proved. So hence proved. So now let us discuss the second property of this particular parallelogram, where second property states that opposite angles of a particular parallelogram will also be equal. So I'll just write this particular property. Opposite angles of parallelogram, I'll just write this like this. So opposite angles of parallelogram are equal to each other. So this is actually the second property and you should actually prove this particular property. So let's see the proof of this particular property. So now let us write a parallelogram image, like we'll draw a figure of a parallelogram and we'll name this as A, B, C, D. Here also we'll draw a diagonal from A to C and we'll actually test the opposite angles are equal or not in this particular parallelogram. So the given information is that this is actually a parallelogram, so opposite sides should be parallel to each other. Now, since opposite sides are parallel to each other, we will actually prove the same property which we proved for the previous property, like the same ASA property which we took to prove that triangle ADC and ABC are similar. So if you use the same property, then here also you can give name as 1. So if you give this angle as 1 and this angle as 2, this angle as 3 and this angle as 4, then here since AB and DC are parallel to each other, here 2 will be equal to 3. Similarly, AD is actually parallel to BC, hence 1 will be equal to 4. And here actually AC is actually equal to AC, because ABC and ADC have common side as AC, so this ABC also has AC as its common side and ADC also has AC as its common side. So that's why AC is equal to AC. According to AAS or ASA, angle side property, this particular triangle ABC is actually congruent to, or it is actually similar to triangle ADC. Since it is similar to triangle ADC, this particular angle should be equal to this particular angle. That shows angle B of this particular parallelogram is actually equal to angle D. Now, we have proved one particular opposite angle is equal. We should prove other pair of opposite angles are also equal. So for that again we will draw the same parallelogram and we will take diagonal in the other direction. So now we have taken diagonal in this particular direction, like we have drawn AC as common side and that was our first diagonal. We will now take second diagonal, that is actually from ABCD. If we name this as ABCD, then diagonal will draw from D to B. So now this BD will act as a common diagonal of triangle ADB and BCD. Now we have two different triangles named triangle ABD and triangle BDC. So in this particular triangle ABD and BDC, we have BD as common angle. So BD is actually equal to BD, and here we will actually name this as 5, this angle as 6, this angle as 7 and this angle as 8. Here also AB is parallel to BC, this also acts as alternating angle. So 5 will be equal to 8 and here AD is actually parallel to BC. So this 7 will be equal to 6. Since AB is parallel to DC, so 5 will be equal to, the angle 5 will be equal to angle 8. Similarly, here AD is actually parallel to BC. So since AD is parallel to BC, here angle 7 will be equal to angle 6. So you have got one side common, two angles as equal. So that means according to ASA property, again this particular triangle ABD is actually similar to triangle BDC. That means this particular triangle and this particular triangle have become a similar triangles. So that shows here angle A and angle C are also equal to each other. So that means according to ASA property, we have proved these two triangles are similar. So angle A should be equal to angle C, since triangle ABD and triangle BDC, this is actually D. So BDC is actually similar to each other. So A is actually equal to C, and we have also proved that B is actually equal to D. So B is equal to D and A is also equal to C. That shows opposite angles of a particular parallelogram are equal. So hence we have proved this particular property. So you can write hence proved for this particular property. So now we will look at third property of this particular parallelogram. So here third property states that adjacent angles of a particular parallelogram, so adjacent angles of parallelogram are supplementary. So are supplementary. Supplementary means it will be actually equal to 180 degree. That means if you add adjacent angles of a parallelogram, that should be equal to 180 degree. So that is actually the third property of a parallelogram. So now let us actually consider a parallelogram like this. The interior sum of interior angles of this particular parallelogram will be equal to 360 degree, because this is actually a quadrilateral. So we have 1, 2, 3, 4. Let's say we have three angles. One is 1, 2, 3, 4. So if you add all these particular interior angles of this particular parallelogram, then that will be summed up to 360 degree, because this is actually a four-sided polygon, which is a quadrilateral. So now we know that 1 and 3 are equal according to property 2 of I'll just write here. So according to property 2 of this particular parallelogram, angle 1 should be equal to angle 3 and angle 2 should be equal to angle 4, because opposite angles in a parallelogram are equal. So let's say 1 and 3, let us name 1 and 3 as x and 2 and 4 as y. So that shows here we have x is equal to x and y is equal to y. Here 1 is there, so 1 and 3 acts as x, so it will become x plus y plus x plus y is equal to 360 degree. Here x and x are opposite angles, y and y are opposite angles of that particular parallelogram. So this will actually sum up to 2x plus 2y is equal to 360 degree. So if 2x and 2y is equal to 360 degree, so now you can see 2 is common for this particular 2x and 2y. So you can take this 2 common outside. So x plus y will be there inside. So I have just taken that 2 common from 2x plus 2y. So which is equal to 360 degree. So in the RHS there will be 360 degree. So this 2 is actually into 2. So if you bring this into 2 to RHS, then it will become divided by 2. So x plus y is actually equal to 360 degree divided by 2. So 360 degree divided by 2 will be 180 degree. So here you can clearly see x and y are two adjacent angles, because opposite angles are same. So that's why opposite angles are x and x, y and y. So x and y will be adjacent angles. Here you can see in this particular parallelogram 1 and 3 are equal, which is actually named as x and x. Similarly 2 and 4 are actually equal to each other. So 2 and 4 were named as y and y, because they are same. Because this is a parallelogram, according to property 2, opposite angles are equal. So y is equal to y, x is equal to x. So here you can see adjacent sides are x and y. Here also you can see adjacent side is x and y. Here also you can see adjacent side is x and y. Here also you can see adjacent side is x and y. And the sum of those two adjacent angles we are getting as 180 degree. Adjacent sides of parallelogram are supplementary. So what do you mean by supplementary is that if you actually add those two adjacent angles, it should be equal to 180 degree. So if it is equal to 180 degree, then those two angles are known as supplementary to each other. That means if you add those two angles, it will become 180 degree. So here in this property 3, we have adjacent angles of a parallelogram are supplementary. Here also we are proving the same. The sum of those two particular adjacent angles is 180 degree. Hence x and y are supplementary to each other. So this particular x and y is actually supplementary. So hence we are actually proving the third property. Diagonals of a parallelogram, there are two diagonals in a parallelogram. So those two diagonals bisect each other. So diagonals bisect each other in a parallelogram. So diagonals bisect each other in a parallelogram. So if you consider a parallelogram ABCD, so to prove this particular property, we will consider a parallelogram named ABCD. So this is that particular parallelogram which has named ABCD, and there are two diagonals in this particular parallelogram. One is from A to C, the other is from D to B. So here you can see there is a intersection point of these two diagonals. So here they are actually saying diagonals are bisecting each other. Bisecting means whenever two line segments intersect each other, it should actually divide the other line segment into half. then only that shows that particular line segment is actually bisecting the other line. Here also, if AC is actually bisecting DB, means this particular line, so let us say this is O, then this OB should be equal to OD and AO should be equal to AOC, because we have to prove that. So the meaning of bisecting each other is that two diagonals are cutting each other into exactly half. That means AO should be equal to OC and DO should be equal to OB. So one particular diagonal is cutting the other diagonal into half and the other diagonal is cutting the other diagonal into half. So these two diagonals are cutting each other into half. So that is actually known as bisecting each other. So here we should actually prove diagonals are bisecting each other. So to prove this, we should actually prove AO is equal to OC and DO is equal to OB. So the only way to do that is that triangle DOC and triangle AOB should be similar to each other. If you prove that, then the sides will be equal to each other. So let us take triangle AOB and triangle DOC. Let us prove these two triangles are congruent to each other. We have a parallelogram. So in a parallelogram, opposite sides will be parallel, and according to property 1, opposite sides should be equal. So according to property 1, I'll just write prop 1. So according to property 1 of parallelogram, opposite sides should be equal. So here AB should be equal to DC. So AB is actually equal to DC. So we are actually considering triangle AOB and DOC. So in that particular triangle, one particular side is actually becoming equal. That is, AB is actually becoming equal to CD or DC. Now we know that this particular AB is actually parallel to this particular DC. That means if we name this particular angle as 1 and this particular angle as 2 and this particular angle as 3 and this particular angle as 4, then since AB is parallel to DC, these two angles should be equal. So angle 3 and angle 4 should be equal, since AB and DC are parallel to each other. They are alternating angles. They act as alternating angles. Hence, angle 3 should be equal to angle 4. Similarly, here AD is also parallel to BC. Hence, this 1 and 2 acts as alternating angles, and hence 1 and 2 should be equal to each other. So here AD is actually parallel to BC. So since AD is parallel to BC, angle 1 should be equal to angle 2. So here you have got one side equal, two angles equal. So according to ASA criteria, so according to ASA property or ASA postulate, so here according to ASA postulate, we have got this particular triangle AOB. So triangle AOB is actually congruent with triangle DOC. So that shows the other remaining angles and sides should be equal of these two particular triangles. That shows AO is actually equal to OC and OD is actually equal to OB. Since here we are getting, since triangle AOB is similar to triangle DOC, here AO should be equal to OC and DO should be equal to OB. This particular condition shows that diagonals of this particular parallelogram are actually bisecting each other, because AO is actually is equal to OC and DO is actually equal to OB. So here actually diagonals of this particular parallelogram are bisecting each other. Hence you have proved the fourth property of this particular parallelogram as well. So rhombus is also a form of kite, but here not only adjacent sides are equal, here all sides of rhombus are actually equal. So here if you consider a rhombus like this, then all sides of this particular rhombus should be equal. So assume this as a quadrilateral which has 4 different sides, then all these sides should be equal to each other. So if all sides of a particular quadrilateral are equal, then that particular quadrilateral is a rhombus. But here in rhombus there is no condition of interior angles becoming equal to each other. Interior angles can be different. but sides should be same. All sides should be same. So you might be knowing that square also has all its sides equal. Here in square, all interior angles are also equal, all sides are also equal. Hence, square can also become a rhombus, but rhombus cannot become a square because rhombus has all sides equal, but there is no condition that all angles should also be equal. So, hence, all rhombus cannot be square, but square is always a rhombus. So, there is one property in this particular rhombus. So let us discuss the property which is there in this particular rhombus. So the property of this rhombus is that diagonals of rhombus, so if you draw two diagonals in a rhombus, then those diagonals will be perpendicular bisectors of each other. So here actually this particular diagonals are bisecting each other, at the same time it is actually perpendicularly bisecting each other. That means one particular diagonal will be perpendicular to the other diagonal. So let us consider a rhombus like this. So if we have a rhombus like this, so there is two diagonals which are actually bisecting each other like this. So let us say this particular rhombus is named as ABCD, and this particular intersection of two diagonals is actually O. So now let us consider triangle AOD and triangle AOB as our two triangles. So let us consider these two triangles. So the one particular triangle is actually AOD and the other triangle is actually AOB. So we are considering these two triangles. So I'll prove these two triangles are congruent to each other. Now AO is actually a common line for these two particular triangles. So AO is actually equal to AO. So this one particular side is actually becoming equal. So since this is a rhombus, all sides should be equal to each other. So then this particular AD should also be equal to AB, since this particular diagram is a rhombus. So AD is actually equal to AB. So if all sides of a rhombus are equal, then you should always remember the opposite sides of that particular rhombus will also be equal. So hence it is also a parallelogram as well. So rhombus is actually a parallelogram as well. But in parallelogram, there is no restriction that all sides should be equal. Only opposite sides will be equal in parallelogram. But in rhombus, opposite sides will be parallel to each other. At the same time, all sides will be equal to each other. So here rhombus is one kind of parallelogram. So since this particular rhombus is a parallelogram, diagonals are actually bisecting each other. So here we can see that this particular figure ABCD is a parallelogram, and we know according to property 4 of that particular parallelogram, we know that diagonals bisect each other. But here we are actually proving it should be perpendicular bisectors. So the main goal in proving this particular property is to prove that these two diagonals are perpendicular to each other. Here actually rhombus is a parallelogram as well. So diagonals bisect each other in a parallelogram. Whether it is perpendicular or not, that we'll be proving later. So here actually, since this is a parallelogram, diagonals are actually bisecting each other. So here diagonals bisect each other according to property 4 of parallelogram. Diagonals bisect each other. So here BO should be equal to OD according to property 4. So BO is actually equal to OD because this is actually a form of parallelogram. Hence diagonals are bisecting each other. So here you can see yes, yes, yes. So side, side, side postulate is actually applied to prove these two particular triangles are congruent triangles. So according to SSS property, that means side, side, side are equal. Like sides of all three sides of a particular triangle are actually equal. So that shows triangle AOD is congruent to triangle AOB. So if triangle AOD is congruent to triangle AOB, so then this particular angle AOD and this particular angle AOB should be equal to each other, because these two triangles are actually congruent to each other. So this shows here angle AOD is actually equal to angle BAOB. So angle AOB. So here angle AOD is actually equal to angle AOB. So sum of angle AOD and angle AOB will be 180 degree because AOD and AOB are linear pairs of this particular straight line. So that shows here AOD and AOB are equal, and AOD and AOB, the sum of AOB and AOB is equal to 180 degree. Here, since AOD and AOB are equal, we can write this as 2AOD because AOB is actually equal to AOD. So here AOB is equal to AOD. Hence I can write this AOD plus AOB as 2AOD. So that shows that is actually equal to 180 degree. So AOD is actually equal to 180 degree by 2. I'll take this 2 to right hand side. So that will be equal to 90 degree. So we are actually getting AOD as 90 degree. So if AOD is 90 degree, since AOD is also equal to AOB, so AOB is also 90 degree. Since AOD and AOB are linear pairs, so this I am writing just because AOD and AOB are linear pairs. Since they are lying on the straight line, so the sum of those two should be 180 degree, and those two are equal as well. So that shows those two angles should be equal to 90 degree because AOB is actually equal to AOD and sum of AOB and AOD is 180 degree. So when you solve that, you are getting AOD and AOB as 90 degree. So this shows diagonals of rhombus are actually perpendicular bisectors of each other. So here actually the bisection of these two particular diagonals are happening perpendicular to each other. So this is one particular property which you have learned for this particular rhombus. So now let us move to the next quadrilateral, that is actually rectangle. So you might be knowing rectangle, the opposite sides of rectangle are equal, and the angles, like all angles of this particular rectangle should be equal to 90 degree. So opposite sides should be equal and all angles should be equal to 90 degree. So only this particular quadrilaterals are known as rectangle. So here one thing you should remember is that even square can also be a rectangle because square also have all its angle equal to 90 degree, and for square also opposite sides are equal. Not only opposite sides, all sides of square are equal. So this is actually satisfying the rule of rectangle as well. So square can also be a rectangle, and this particular figure can also be a rectangle where opposite sides of that particular quadrilateral is equal and all the angles of that particular quadrilateral is equal to 90 degree. So the difference between parallelogram and rectangle is that parallelogram doesn't have a rule of having all its interior angles equal to 90 degree. But there also opposite sides should be parallel to each other and the opposite sides should be equal. Here in rectangle, opposite sides are parallel, opposite sides are equal as well, but all angles of this this particular quadrilateral should be equal to 90 degree. Then only it will form a rectangle. So even a rectangle is a parallelogram, but parallelogram is not a rectangle. Even square is a parallelogram, but parallelogram is not a square. A square is a rectangle, but rectangle is not a square always. So you should actually remember all these points. So there is one particular property in this particular rectangle as well. So this property states that diagonals of this particular rectangle will always be equal. Diagonals are equal in a rectangle. So if in a rectangle, if you consider two particular diagonals, then in that particular rectangle diagonals will be equal. So to prove this, we will actually take a rectangle as our example. So we'll actually draw a rectangle. So let us name this particular rectangle as ABCD. So we'll draw two particular diagonals in this particular rectangle. So one is A to C and the other is D to B. Now let us consider triangle ADC and BDC. So that will actually look like this. So this is one particular triangle which is actually ADC, and the other triangle is actually looks like this. So which is actually BCD or BDC. So you can see this particular rectangle, I am considering this particular triangle ADC and I am considering this particular triangle ABC. So that looks like this. So here you should remember this DC is actually common side of this particular rectangle. So in rectangle, opposite sides are actually equal. So here in triangle ADC and triangle BDC, here DC is acting as common line. So DC is equal to DC and opposite sides are equal. Hence AD is actually equal to BC, and you can see that all angles of this particular rectangle is equal to 90 degree. So this particular angle D and this particular angle C is equal to 90 degree. So here angle D is equal to angle C is equal to 90 degree. That shows once two sides and one angle in these two triangles are equal. That shows according to SAS postulate, that is side angle side postulate of two triangles. So these two triangles are actually congruent to each other. That shows triangle ADC is actually congruent to triangle BDC. So since these two triangles are congruent to each other, then this particular AC and this particular BD should be equal to each other. So here AC should be equal to BD. Since this particular triangle ADC and BDC are congruent to each other, AC is actually equal to BD. So here you can see diagonals are equal. So in this particular diagonals, in this particular rectangle, two diagonals AC and BD are actually equal to each other. So hence you have proved this particular property. So you can write hence proved. So after learning about this rectangle, you have another quadrilateral which is actually known as square. So square is a very simple quadrilateral which has all its sides equal and all its angles are equal to 90 degree. So this particular quadrilateral is actually known as square. So a square can be a trapezium, a square can be a parallelogram, a square can be a rectangle, a square can be a kite, and a square can also be a rhombus, because all the properties of this particular rhombus, all the properties of kite, all the properties of rectangle, all the properties of parallelogram and all the properties of trapezium is actually satisfied by square. So square can be a trapezium, it can be a kite, it can be a parallelogram, it can be a rhombus. But all rhombus are not square, all kite are not square, all rectangle are not square, all parallelogram or all trapeziums are not square. But squares can be all of those. So this was actually the second part of this particular quadrilaterals chapter. So there is one more part of this particular quadrilaterals chapter where I have discussed exercise 3.3 and 3.4 in that particular part 3. So after watching part 1 and after watching part 2, that is the current video, you should also watch the part 3 video of this particular quadrilaterals. Then only you can understand this particular chapter quadrilaterals. So this is all there in this particular video. So like this, I will be uploading more and more physics, chemistry and mathematics videos in this particular YouTube channel. Please subscribe to my YouTube channel if you want to learn physics, chemistry and mathematics. Stay tuned with my YouTube channel. Thank you.